In this video, we're going to go ahead and look at power functions, which essentially are polynomials. They're very simple polynomials that essentially only have one x term in it being raised to a particular power. And because they only have one x term, we can go ahead and treat them in a sense like transformations that we've seen before. So we'll be using transformations to graph these power functions. So as you can see with our graphs here, we essentially have two types of power functions that we could run across. So some of these we actually have seen before. So there's power functions that have an even power on our x. So the example we've seen in the past is x squared, which has that very characteristic u parabola-like shape to it. And the interesting thing is that all of the power functions that have even powers will essentially act the same way. They will also have kind of a U-like shape to them. And really the only key difference is that because my power is larger, that our values for y are getting also very large very quickly. So if you compare these three graphs, so the green colored sort of graph here is our x squared, the traditional parabola shape we're used to. The x to the fourth graph is the orange graph, and so we can see that it's a lot more dramatic of a U shape, that around 0 it's getting a lot more flat or closer to the x-axis. And then once we pass 1, our tail ends are increasing very, very quickly. And that's happening because of the nature of the x to the fourth, that if I have a fractional value and I raise it to the fourth power, that it gets very small, right? So values close to 0 are a lot smaller than if I had just squared them. And then values bigger than 1 are going to increase very, very rapidly when we raise them to the fourth power. So it's a very distinctive kind of flat U shape that happens. And it becomes even more dramatic the higher that our power goes. So when I go to x to the sixth, which is this blue graph, we can see that behavior is even more pronounced, that around 0, my graph almost looks completely flat. It's not, though. There is some changing of values, although very, very small differences. And then very rapidly, it's going to increase and get very large very quickly. So any function that has just x being raised to an even power will kind of have this U shape occurring to it. If we have odd powers of x to the third, to the fifth, or to the seventh, those also have the same sort of characteristic behavior. The x to the cubed we've seen before, it has kind of that elongated S shape to it. And very similarly, when we increase the power to a power 5 or power 7, we have that same sort of behavior happening, that around 0, my graph is a lot flatter. My y values are a lot closer to 0 or a lot lesser in value because of the higher power occurring to those fractional values. And then once we pass 1, our values again are increasing very, very rapidly. So we can see, and it's almost very subtle, that when I went from the green graph, which is x cubed, that again it's increasingly far more rapidly on our tail ends here for x to the fifth, and x to the seventh even more so. So these will all kind of have the S-like shape to them. The key difference is just how quickly those ends are going to be increasing with those higher powers. So now that we've talked about those power functions, we can go ahead and look at transformations on those power functions. So because the nature of a power function is it only has one term, with x being raised to a power, transformations work very easily on them. And we saw that before when we did transformations on the x squared and x cubed graphs. So here's some that maybe we're not so familiar with. We'll try some of the other power functions and using transformations on them. So this first one, what I want to go ahead and do is rewrite this in the standard polynomial format so I can more easily identify the transformations that are happening. So all I did was reorder and put x to the fifth as the leading term. So the first thing we want to identify is the parent function, the type of function that we're going to be performing these transformations on. And so the parent function is our generic power functions that we saw in the last slide. And so here would be the x to the fifth graph. And that's what we see graphed here on the screen in purple. Now, if you notice, I didn't include that many values of x, and that's because the nature of this x to the fifth is that it's going to get very large very quickly. So once we go past an x value of 1, it gets incredibly large, right? If I did 2 to the fifth power, I believe that's 32. Let's check that out. So 2 to the fifth power, yes, it's 32. So my points there are getting very large very rapidly. And so I'd have to dramatically zoom out on this graph to get a y value of 32, and we'd really kind of lose the behavior around 0. So that's why I kept this graph very tight, because the tail ends just get very large. It's the same behavior, it's just getting very large, either going down on the left and increasing on the right. So there's my parent function already graphed. So now we can look at our transformations. So the first transformation is going to be this negative that's applying to the x to the fifth. And because I don't have parentheses written down, that's showing that that negative is happening after the x to the fifth happens. So it's actually outside my parent function. So this would be a reflection over the x-axis. And how I knew that is because what is really happening here is we're taking x and we're making it, or pardon me, this would be y now, right? It's outside the parent function. So I'm taking my y and making it negative. So if I had a positive y, now it goes negative. That's going to reflect it over the x-axis. Then the second transformation is going to be this +1. That's also occurring outside our parent function. So that's going to affect our y's. So this is going to be a movement up by 1 unit. So let's first do that reflection. So I'm going to take these 3 key points and perform that reflection over the x-axis. So currently my value for y is 1, because 1 raised to the fifth power is 1 again. And now I'm going to reflect it. It'll be 1 unit on the other side of the x-axis. So that would put it down at -1. 0 is on my x-axis, so that would stay in the same location. And then the value that's at -1, which happened because -1 raised to the fifth power is -1, that would get reflected up by 1 unit to become +1. And I could actually show with maybe dashed lines here, because this isn't my final graph, there would be just the reflection over the x-axis. And then we're going to take each of those 3 key points and move them up 1 unit from where they were on the last transformation. And that will be our final graph. So our final graph is going to have that same sort of behavior to the shape, very flat in the center and then increasing very rapidly on each side. So that would be our final transformation. And let's try one of our other variety, which is an even power. So this doesn't quite look like maybe what we think of a polynomial, and it's written this way to assist us in doing our transformation. So we would first identify our parent function, and in this instance, it's going to be y equals x to the fourth. And really, I was just looking at, we have this x happening, seeing what power would be applied to x. It's x to the fourth. And that's the graph that we currently have graphed in purple. And for the same reason as the last function being kind of very tightly zoomed in on the graph, that's the same reason that we're doing it here, because when I raise any value past 1 to the fourth power, it gets very large very, very quickly. So 2 to the fourth power is 16. And so, yeah, I'd be having to zoom out very drastically on my graph to capture that 16, and I wouldn't be able to see the behavior around 0 very well. So we'll just use our 3 key points at -1, 0, and 1 to keep track of our transformations. So the first transformation that would occur is this subtraction on my x. So it's acting inside my parent function on the x itself. So that's a horizontal change. So this would be movement left and right. And anything horizontally done for our transformation is counterintuitive. So even though I see a -1 and think that's going to be a movement left, it's actually the opposite. It's going to move it to the right 1 unit. And then we have this 1/2 happening. So I would have my power 4, which is our parent function, and then it would get multiplied by 1/2 outside that parent function. And so this multiplication by 1/2 is really going to take essentially my y values, wherever I am on those y values, and they're going to multiply by 1/2. And then visually, what does that look like? Well, it's going to be a vertical compression. And what makes it a compression is that my multiplier is less than 1. So it's going to move all of our y values to be smaller than what they were before, and that makes it look like it's being flattened towards the x-axis. So let's first do that transformation to the right one. So I'm going to take all of my 3 parent function key points and move them to the right one. And again, if it's helpful, we can show the graph kind of as a dashed line so we can visualize it a little bit better. So there's my graph, moving to the right one. And then we want to take those 3 values and we'll multiply them by 1/2. So here I'm going to kind of keep track of my values. Let's do a little bit of a table of sorts just to keep track of what's happening to y. So this first point, when x is 0, his y value was 1, but we want to multiply that by 1/2. And so for that same x value of 0, now I'm going to be at 1/2 instead of 1. The next key point was at 1. Its y value was 0, which when you multiply it by 1/2 doesn't affect it. It stays at 0. So that will stay in the same location. Then at 2, I also had a y value of 1, which when multiplied by 1/2, again yields a 1/2. So although this graph was pretty flat to begin with because it was an x to the 4th, it got even flatter because of that 1/2. So this is going to look that same U shape, just very, very flat around what we would call the vertex, the lowest point.